Hello, and welcome to today's tutorial on how to solve quadratic equations through a method called factorization. Part 1. Before we start, let's get an idea of what this means. So, let's start with the most basic. What is a quadratic? This is probably the newest term to most of you. The word quadratic just means that the highest exponent is 2. So below we have shown an example of a quadratic. In the expression, the example is x squared plus 3x plus 2. That is a quadratic because the highest exponent is a square, which is x squared. So we find that in quadratics, there is always a pronumeral with a square term. Let's give another example. 3x squared plus 5x minus 2. This is another quadratic because even though there is a coefficient or number before the x, there is still, as the highest exponent, x to the power of 2. If we compare the two quadratic examples that we have given, we find that it is generally in the format of ax squared plus bx plus c. We know that a cannot ever be 0 because the defining factor of a quadratic is that it must have a squared term. However, bx and c don't always have to be present. B and c could equal 0, which could give us a quadratic such as x squared equals 0, or x squared plus x equals 0. Now you might be wondering, how come the general format only has plus signs? That is because in algebra, it is the coefficient that is far more important, or the number before a term. Now this explains why you can have negative numbers within these quadratics. It is simply that c is equivalent to a negative number. So in the previous example, you could see that 3x squared plus 5x minus 2 had the term c as negative 2, explaining the negative constant. The term constant simply means the singular number. Alternatively, you could say that it is the number with no x attached to it. Now that we know what a quadratic is, let's see it in an equation. Like any other algebraic equation, a quadratic equation is simply a quadratic expression that equals something. An example of this is x squared plus 3x minus 2 equals 0. Now that we know what a quadratic is, all we have to do is solve the equation, which means finding the values of the pronumerals. In most cases, we are looking for the solution to the unknown pronumeral. A simple equation like x equals 5 or x equals negative 1. Now moving on to factorization. Most of you will probably understand factorization as breaking a number into its factors, primary components. It's similar to factorizing a number. Take 42 for example. It's 6 times 7, which is 2 times 3 times 7. We have simply broken the number into its prime factors. When algebraically factorizing, you're simply looking for the two terms that will multiply together to provide you with the quadratic that you want to factorize. Our first method of factorization is relatively simple. However, it only works when the c in ax squared plus bx plus c is 0. What we are trying to do is to take out the common term. In the following example, we have the expression x squared plus 3x. You can see this is a quadratic because it has a squared term. Let's apply the method of bringing out the common terms. We can see that x squared can be broken up into x times x, and 3x can be broken up into 3 times x. In both cases, we can see that x has a coefficient. So x is the common term. This allows us to bring x out of the expression and multiply it by x plus 3 brackets. If you then solve our new expression, you will get x squared plus 3x, which is what we started off with. The reason this works is because of something known as the distributive property, meaning whenever you multiply anything in brackets, you must apply that same multiplier to every number within the brackets. You could think of it like handshakes if you like. In order to join the party, you must handshake with everybody present. That's the same idea with the distributive property within brackets. Let's take another example, such as x squared plus 5x. Again, the common term is x, so we bring x out of the equation to get x times x plus 5 brackets. A slightly harder example is a squared plus half a. The factorization of this expression is the same as the ones we have been doing for the past two examples. With a being the common term, we bring it outside to form the expression a times brackets a plus half. Taking it one step further, we can have n squared plus root 2 times n. The root 2 might look slightly confusing. Fortunately, root 2 is not the common term in this expression. Rather, it is n. So we would bring n to the outside to form n times brackets n plus root 2. However, this method won't work for equations that have a term c. So we turn to a method called cross-factorisation. Within a three-term quadratic, say x squared plus 5x plus 6, what we want to do is split them into the form of ax plus b bracket multiplied by cx plus d bracket. By algebraically expanding these numbers, you would get acx squared plus bracket adx plus bcx close bracket plus bracket b plus d close bracket. By dragging out the common terms, we return to the form that we have been used to, which is ax squared plus bx plus c. We can conclude from this that in order to factorize a quadratic, you would have to split the coefficient of the x squared into two terms that multiply exactly to that coefficient, and factorize the constant into two different factors that would multiply exactly to that constant. We want the diagonal products of these two factors to add up and equal to exactly the middle term. If that all sounded confusing, don't worry, we will show it in the following example. To factorize the quadratic equation 3x squared plus 5x plus 2, we would first find two terms that would multiply together to equal 3x squared. In this case, you would only have the option of 3x and x. However, the order that you put these terms in will be important, and we will show later why that is. For the constant, you can only split it into 2 times 1, as 2 is prime. If we were to call the factors of the square term a and b, and the factors of the constant c and d, our goal would be for a times d plus b times c to equal the term in the middle. So we find two numbers, a and c, that multiply to 3, and find two numbers, b and d, that multiply to 2. And 5x being in the middle, we know that the products of the two diagonals must add together to equal 5x. We really only have two ways to do this since we are looking for integer solutions. For 3x squared, you can split it into 3x and x. For 2, you can only split it into 2 and 1. Now drawing back to our algebraic expression of the quadratic factorization method, if we allow a to be 3x, b to be x, c to be 1, and d to be 2, after the cross multiplication, you would result in a middle term of 7x, because 3x times 2 equals 6, plus 1 times x equals 7. However, we want 5x, so how about we switch this around? We let a still be 3x and b still be equal to x. However, we change it so that c is equivalent to 2 and d is equivalent to 1. This will result in 3x times 1 plus 2 times x, which adds to 5x. Now we simply pair a and c together and b and d together to solve our quadratic expression. To conclude, you have just factorized the quadratic into brackets 3x plus 2 close brackets times x plus 1 brackets. You could always check your factorization by expanding the brackets and ensuring that the quadratic resulting from the expansion is the same as the quadratic you started off with. Let's work through another example. Take the quadratic x squared plus 7x plus 6. The x squared can only be separated into x and x. Thus, the question now remains is what factors of 6, when added together, results in 7? 2 times 3 equals 6. However, 2 plus 3 equals 5. That's not the number we're looking for. However, you can find that 1 times 6 equals 6. However, 6 plus 1 also equals 7. So we find that we can now factorize into x plus 6 and x plus 1. Let's try a slightly harder example. Take 3x squared plus 8x plus 4. The constant now has many more options for how to divide it into factors. 3x squared stays relatively simple, splitting only into 3x and x. However, for 4, you have options such as 1 times 4 and 2 times 2. Now that we know the options for the factors, we simply need to assign them to the A, B, C, and D format. Throughout the following commentary, we shall keep A and B the same, with A being 3x and B being x. If we allow C to be 1 and D to be 4, we would have 3x times 4 plus 1 times x, which would equal 13x. We could reverse the order with C being 4 and D equaling 1. This would result in 3x times 1 plus 4 times x, which would add to give us 7x. Closer, but still not the answer that we want. At last, with no other options left, we can see that C equaling 2 and D equaling 2 would result in the correct answer with 3x times 2 plus x times 2, which equals 8x. Thank you for watching the first part of the tutorial on how to solve quadratic equations. Press the link in the description for part 2.